Alrighty, folks. Welcome to Techniques for Wielding Data and Behaviors. I'm Mike. I'm going to be your speaker today. Thank you so much, NDC Toronto, for hosting me for a talk again this year. It's very exciting to be back in Toronto. And today we're going to have a little bit of fun talking about playing with data, thinking about some techniques for how to wield data and behaviors and so on. So feel free to ask any questions at any point during this talk. The source code that I'm going to be showing is available on GitHub if you'd like to follow along later. And I'll post these slides, of course, on my website. You can search Mike Shah and you'll probably find me there. And that'll be the easiest way to follow along. Here's a little bit about me. Hopefully you read the abstract. But again, we're going to be talking about data and different ways to play with data today. That's our goal. A little bit more about me. I teach. That's my primary role these days over at Yale University in computer systems, computer graphics, these types of courses. And then I do various trainings on occasion, or so you can find me. And then, of course, talk to me about some other fun stuff after the talk. I also do a lot of YouTube, so if you enjoy my talks, you can find me on YouTube, and I do a variety of programming content. I love programming languages. I love talking about basically anything computer science. It's a technical YouTube channel, so feel free to check me out there. All right, so that's enough about me. Let's go ahead and get on to the talk here. And again, the goal today is to just open your mind a little bit with how you think about the data that you have in a program, how you can maybe constrain or unconstrain yourself depending on what programming language that you're working with. And I'm going to be showing various code today, various things that are considered design patterns in some languages, or maybe things that are just built into programming languages themselves. So we'll see a variety of different tools and techniques today. Again, your goal going to be to just play with bits, because at the end of the day, that's all a computer is. You'll hear me say that a few times here. So that's kind of where we could start this whole process when we think about the data on our machines. We could start with, well, sand. We're kind of teaching sand how to think, whether that's scary or not. You be the judge. But that's where this all starts from, right? But okay, I don't want to take you all the way back. That's going to take a little bit too long, right, if we start from sand and computation at that level. And if you do want a great book on starting from that level, Code is a book that I've read that's very good. So let's accelerate ourselves just a little bit here and start with at least having a computer. Okay, so again, a computer with some definition of what a computer is, machine that basically can be automated to do things. That's what, well, most of us in this room are developers here at various levels. So again, fundamentally, all a computer does is transform data. Right? We've taken some input, produce an output. We can think of it mathematically, like with a function, for instance. But again, we just, at the end of the day, are transforming data. So again, as mentioned, we basically just have a box of bits that we're transforming when we're executing some program. We can kind of reshuffle things in different ways. We come up with different algorithms to do this. So programming itself is just a very, very creative craft. And of course, the engineering part of it in software engineering is, how do we get the desired result, prove things about correctness, organize large code bases. So it's a really, really fun field for us to be working in. I still feel incredibly lucky to be in this field and to have found it. Anyways, it's, as you control bits and have fun, you kind of, well, sometimes I feel like this if I'm being really good here in the matrix, seeing the bits and shifting things. And I made this reference once in class a few years ago, and people said, "What is this movie?" I said, well, it's not that old, so thank goodness for the new one that came out. People can kind of understand seeing the matrix, seeing the bits. Okay, so let's kind of keep progressing forward a little bit here. And okay, so we have these bits that we're going to transform in our computer. Of course, a computer, something that looks like this. If you've ever seen, this is a model of a Turing machine. So starting from, again, sort of a scratch level, gone from sand to a computing machine to what does it actually look like? Well, again, we're just sort of looking through data and transforming those bits and bytes. Okay, we have more efficient tools, random access memory, these types of things to access memory, maybe more efficiently here. But again, at a minimum, this is what we need for our computation. Some way to read, write, jump to bits, test bits, maybe conditionals. That's what we'd say Turing sort of complete languages by some definition, so that we can actually do some work with these machines. Okay, so moving a little bit more forward here, then we have programming languages that help us express how to do these computations. You can see on the right here, there'll be some set of characters that we can provide into our programming language to perform operations and transform data. Here's an example programming language here. Has anybody seen this? Don't shout out the name, but you kind of know this is an example programming language. It's probably not a very expressive programming language, but it is sort of this Turing complete. You can write sort of any sort of programming language with this sequence of symbols here. And it's interesting for different reasons, and we'll actually kind of revisit or finish with this in some ways of how compressible we can represent this knowledge here, again, to do computation. But again, let's move just a little bit higher level, because that's probably what we're more interested in as far as programming languages. I'm going to move us in our programming language history to the B and C programming language. And just by a show of hands, how many folks were expecting to learn about the B programming language today? Nobody? Oh, okay, yeah, it's a pretty old language, so, so let's go ahead and see what that looks like here. So again, our goal is to be able to express computation, be able to do some work in our programming languages with these tools. And the B programming language came out around in the 60s, and it gave us many of the capabilities that are going to look pretty familiar to what we have today here. I mean, you can see a snippet here from the Wikipedia of some of the features of the B programming language. We've got variables, so global, local variables. Auto here actually just means automatic storage, so stack storage, not the same thing we have in C++ or other languages for deducing the type. B just has integers, so everything is an integer. Again, I guess that's how everything's represented on our machines anyway, so that makes sense. We have arrays, different types of arrays, or in B they call them vectors. That's not related to how std vector is called in any way in C++, that's just how they refer to them there. So a little bit more story on that, but we have ways to group contiguous chunks of data dynamically or on the stack. We've got functions that we can declare that take in inputs and outputs, and control flow. So a relatively complete programming language, while, repeat, go to, if, for controlling how we move around. Now, anyways, so that's a little brief history lesson on B, kind of an interesting language, somewhat dynamic in how it is, but you can kind of see or maybe appreciate where C evolved from, right? So the next language in our evolution is the C programming language. And here's our modern day, I guess, hello world in the C programming language. And C is, of course, still something that maybe you're using today. It's considered our sort of lingua franca. It's the common language that we talk to, common interface. And it basically has all the tools, or most of the tools, I would say, that we need today to express a lot of computations. Okay, some of them we have to invent, which we'll do today, kind of playing around with our bits and bytes. But C has just enough, and maybe that's why it's sticking around, beyond legacy code reasons. So, extending on the B programming language, C gives us some ways to play with our code with some, more constraints. It's got a type system. We can argue about how strong that is or how enforced it is, but there are types. So if I say something's an integer, it's an integer, a char is a char, and so on. We can define our own data types, so things like structs, we can aggregate data, unions, and of course we have control flow and so on. And there's a whole story about portability and a preprocessor and these things that maybe explain why we're still having or using C for systems. Okay, but I'm going to show most of my examples today in D. There's going to be a little bit of C++. It doesn't really matter if you understand, as long as you understand some high-level programming language today, you'll be able to follow along. But we'll continue our sort of journey in B to C to D. Not to E, we won't make it. But that'll be sort of our evolution here. Okay, so let's start wielding our data and data structures here to do something. So we're going to sort of think about our tools that we have or can hold on to. And we're going to start with the data part first. Let's just look at some data here. Again, things that I think this audience here will know, but just to give us a little bit of a baseline. Right? And thinking about in our systems that we have, our high-level languages, most of our C family languages, we have some sort of type that's associated with a variable that we create, okay? And that tells us how we're going to create that type, maybe on the stack or the heap, and how to interpret those bits as integer bytes here, okay? And then in C++, we can print it out. Now, of course, one of the first things we can do to start playing around with our data is to say, well, we've got the underlying data, but let's cast it or treat it, interpret the data in some other way. So C++ has a lot of different tools, so that's why I'm using as an example here for saying, well, let's reinterpret that value here as a character. So we can cast that type. We can use other things like reinterpret cast that maybe express in a C++ way that we're changing these bits, or maybe a bit cast, or static cast, or dynamic cast, so many different ways to reinterpret and shape how we want to look at this data. Okay, so this is our way of saying, well, we've got these languages that have static types, but we're just going to unconstrain ourselves and think of this data in a different way. Okay, so we're going to change what the actual type or how it's interpreted. Okay, the underlying data is the same, but we're going to change something about it. Okay, so let's continue playing a bit with data here. I'm switching over to D for most of these examples here. And we can start playing with the bits here. So just starting from the top here, looking at these different integers here. I've got maybe some color value I'm trying to represent, maybe pixels on my screen. Well, at the very top, there are different ways that I can just represent the same data, but in different ways. And maybe that gives me a cue of how I'm going to use the data, maybe how the data is structured, right? 17 doesn't give me much information, but if I break it down into the byte components and hexadecimal or binary, that's kind of interesting to look at. So that's one way I can start playing or signaling what's interesting about this data. Now, the other things I can do here is I can say, well, we have this integer type, but what I actually want to do is, again, use our tool we just learned about casting and start reinterpreting this data in a different way, so as individual bytes. And what I'm doing here, if you haven't seen this type of thing, is I'm basically unpacking the integer into 4 individual bytes here into different components: red, green, blue, alpha values. That's one way that we might represent a pixel on our screen, for instance, in the different components. Okay, so we're just playing with our data here a little bit with some of the different things that we can do. So again, there's this, RGBA, red, green, blue, alpha value, way to represent pixels. But if you've done some work in graphics or printing, maybe you've used different color systems, or even in journalism, you might use different systems. You might say, well, okay, I like these values here. I can compress them in an integer, but maybe I'm representing them in a different way. So again, we can start playing with the data here, and we can do something known as bit swizzling. And this is basically within our integer, rearranging those components. So maybe I want to represent things as blue, green, red, alpha, same data, but I'm swizzling and shaping the data for whatever reason. Maybe my machine that's decoding the video needs it in that format, or passing data around a network and need to flip the bits. But we can do this, again, just to play with all the individual bits here. So I've got some, so I can read the comments, and again, all these examples are posted on how to swizzle bits, but we're just doing some bit shifting operations and some maths on that data to get bits in the right position. Okay, so kind of fun how we can play around with data here. Bonus points if you want to talk about efficiency and go into your single instruction multiple data, so std SIMD or the SIMD library in D you can also use. And also bonus points if you thought that was fun, and I give you your yet second book that you can pick up after this talk, Hacker's Delight. Has anybody actually taken a look at this book before? Oh, it's a great book on little bit manipulation tricks that you can do. I call them tricks, but they're actual real things that you can do that could solve problems and introduce some interesting ideas. So feel free to check that out. All right, so okay, so we've got some data. We've made it up to an integer, 15 minutes into the talk, representing our data, but let's do something a little bit more structured, right? So I can add a struct, a user-defined type, and this time I'm being more explicit with how I'm going to pack the data together. Still the same 32 bits that I've got here, but again, I've broken out the individual fields. It gives me the ordering much more explicitly. Okay, so this is one tool that we can use here. And again, can still use my techniques if I want to, cast the different types and swizzle them or access them in different ways here. In this case, I'm accessing things as an array through the pointer. Again, different tools that we can use to work with our data. Okay, so structs are interesting for structuring our data, but we've also got this other tool, unions. And well, thanks for selecting my talk. There's a whole other talk going on for about an hour on unions on a deep dive here. But we'll get to see them today. But they're an interesting, often forgotten way to play with data, I think. And basically what a union is a tool that says we can pack basically one thing into a set of bytes, and we're going to, sort of as a constraint, say we can treat that value or cast it legally to integer data or character value here. That's kind of how I think of this here. These are constraints that I'm putting on whatever I want to put into value. And the different ways that I could interpret this particular, anything that is of type uppercase value here. Okay, so those are our unions. Now, what's sort of interesting about unions is to say, well, okay, so I've just got this black box of bits that I can play. How would I know how to interpret it? So we can go, one step further, and we can assign to the actual value a type. So now we're saying, okay, I have this thing that's bounded to some number of types here, int and char, two different particular types that we could interpret it, but I want to be a little bit more strict or maybe keep track of that. And again, this is what something like a compiler does for us with a type system. It'll keep track of that. Now, we're pushing responsibility a little bit onto us to keep track of what this type is, but now I have a field within the struct here, and then some second field here where I can treat this in two different ways here. Okay, and we call this a tagged union. And again, depending on the internal type here, we can treat this in different ways as we pass this data into different functions here. Okay, so we've got my switch statement here, the different types that it can be treated as, in which we can, based on the tag of the tagged union. All right, so another way just to think about this, how we're treating the data here, and sorry, the thing's a little bit blurry or out of focus, but we've got the header here tag and the payload. Okay, so that's just another way to think about this. So it's almost like a protocol in some ways that I'm thinking about this union. I've got some header for how to treat this, and then the actual data that I'm going to send along the way. And this can be really useful if you're using tag unions, for instance, for things like events, again, sending and receiving data, and you want to know what type of data you're sending along. And just to give you another view of this, because I wanted to provide some real examples here. In a lot of C libraries, or in particular what I talked about last year at some related conferences, SDL, which is a graphics library, in their event system, you can see they're using unions, and the start of every union, so a little bit more compact, is the actual type. And then anything that could be a field, well, we also sort of match that layout in memory, and we have a type, and then any of the fields that would follow. Okay? So this is another way that you could also structure these sort of tagged unions here and get the type information out. So again, this is kind of a nice example as purely a union here. All right, so let's progress a little bit forward. We've got some of our basic tools. We're starting to play around a little bit with data, maybe shifting how we're thinking about things, maybe thinking about our data in terms of protocols and how we arrange things. But let's move forward in our language history, right, B to C to D. And what does D and C++ give us, and Java, C#, et cetera? Well, they start to give us more fun tools that we can start working with. Okay, there's all the fun stuff with metaprogramming. We get stronger type safety now. We start getting some functional features. But really what I'm going to start by focusing on is the object-oriented capabilities and how we can start playing with those to start, again, wielding our data and data structures here. Okay, so object-oriented programming. Again, we want to sort of build things up from the bottom here and understand how we get there. So if I say, okay, we've got these great new features in these languages, so how do I get to objects? Well, in C, right, you could emulate the object-oriented style programming by basically passing in whatever your type is as the first parameter here. Okay, so again, simple enough here. And again, see we don't have modules or namespaces or fancy things, so int array underscore 0 shows the operation for what we're doing on what the assumed type is, or the first parameter there, some integer array, and then you can pass in your arguments. Okay, simple enough here in C. So here's a example then pushing this a little bit further here and say, well, okay, let's actually make some sort of type here. Let's do something a little bit better here. We're still in C, but maybe a little bit better. I call this a fat pointer here, in which we have the array and the length, which we should pass together, right? And these are things like span and so on that you'll find in C++ or in D. This is how arrays are just passed. They're always pointer and length, so a little bit nicer for us to work with. But as we're creating different types of these functions here, we're still going to pass in the first parameter. I've got an example down here. We'll start to see, again, we have these repeating patterns in our object-oriented programming, things like the constructor, where we're developing the type, and then, of course, we have our behaviors or member functions, where, again, we're acting on the type that is the first parameter. Okay, so, again, stuff that we know here. And I just want to point out here, because we're going to talk about some patterns as they come up here, that when I see this sort of function where I'm making something or constructing something, that's sort of this factory method or factory pattern. Anywhere where we're kind of hiding the initialization, where we're doing our mallocs and news and how the object's created, right? We just want to be able to call this function and return it. So again, common enough pattern, common enough way to work with data. So these are the things that have gotten rolled into object-oriented programming. So let's go ahead and look at this in a object-oriented language. We can see the evolution here, where within our type here, this struct, we've still got our fields, whatever the data is, but now our behaviors are embedded within the struct here. Okay, so we don't have to pass the explicit object that we're working on. Okay, so these are our behaviors, or again, sometimes called methods, member functions in different languages, and then we've got our fields. Okay, great, we know some of that here. So what's interesting about this, or where can we start to play? Well, as soon as I make these objects and I add in the behaviors or the member functions, these are sort of, again, the implied constraints. These are the actions that I'm going to be doing on these objects. So I can zero the array, print it out, increment the values, and so on. But what if I want to sort of, again, unconstrain myself and start doing more interesting things with these objects? So I've got this very concrete object here with the same field, same data types, and so on. All right, so let's wield our algorithms a little bit. So by algorithms, I mostly mean just the behaviors or things that we're going to do with our objects and change them around. And algorithms is, again, a full, semester course, let's say, and there's lots of really cool things that you can do with them. I saw, Connor gave a talk later. Folks should check out Google Translate if you haven't seen it. It's a really cool way to find different algorithms. So I can find some different building blocks that you have here. But what I want to focus on here is unconstraining our behaviors again. Again, playing with, when I have an object, what are the different things that I can do with an object? So let's take something that's maybe dynamic. You're creating something in a game. So I have a game entity here with a name, health, power, and different things that you'd want with a character in a game, or again, something relatively dynamic here. Okay, and we've got our constructor, again, built in here. So we've got our factory, so to speak. Now, provided in this example here, where I'm going to start here is I can have two different versions or two different behaviors here of this attack function. Okay, I'm being a little bit aggressive here, attacking, or moving, or whatever you want to choose. But let's say we have attack here. First version, again, pretty concrete. We just perform whatever this behavior is. Second version, a little bit more interesting here. Right? We've actually parameterized this. We have a argument that we have here, type, and well, in this particular code snippet here, you have the case switch statement here. And if type is 1, we'll do something. If we pass in a 2, we'll do something else. And then maybe we have a default case here. Okay, that's a little bit more interesting. I don't know if I'd necessarily write the code like this, but it's kind of interesting just to say, okay, we can start parameterizing things. But again, what if I sort of totally want to unconstrain myself and say, well, what is the behavior? What are the different types of actions a game entity can do when it's attacking? So what's our tool here? Well, we can use something like a function pointer or pass in a function to attack here. And we call these higher order functions where we can pass in or return other functions from a function. But what's sort of interesting here is then we unconstrain ourselves to what does it mean to, for this game entity to do some sort of attack. We can pass in the behavior as an argument and then pass in any maybe parameters that should be passed in on this behavior here. Okay, so now we've made our capabilities of what a game entity can do much, much more dynamic. And this, again, has some sort of name. We might call this a strategy pattern here, where we're passing in to a particular function, another function to change the behavior. Oftentimes, we might also pass in an object. And again, this can be useful in many different cases. Again, we can think about a dynamic case like a video game here, where we're changing behavior. Maybe you have a sorting algorithm, and you want to change how that sort performs. And so on and so forth. So you can learn a little bit more about the strategy there. Okay, so let's continue unconstraining or just thinking about how we would perform some different things here. So again, we've still got our struct here for game entity. And at this point, we said, well, great, we can just pass in two different functions, things like attack to do things, but why not just have that as a field in our struct here? So we can just pass in, again, function pointers, stood function, function pointer, or ND is defined in line 12, a function here, the different types of actions that we want to assign to different instances of game entity. Okay, and that gets a little bit more interesting, how we sort of bind these behaviors to our game entity, totally dynamic now for what it can do. What's the trade-off? Well, it's totally dynamic, so we can sort of do anything. We don't really know until we've assigned this function what it's going to do, but it gives us ultimately a lot of flexibility in what this type of, again, game entity can do, anything. And I'm using some different tricks in the example for binding. You can sort of default in parameters if you want, using bind or partial to do that, but anyways, that's the note on the bottom. Okay, so anyways, here's an example of the use case here of actually then having this game entity. Maybe you call a constructor or set the constructor explicitly. Within that constructor, you can hook up different behaviors as you need it for each instance of the game entity. Okay, now again, this costs me something because I have to set this up or maybe define some other functions to set up all the function pointers every time, but again, this allows me to be quite dynamic in what I'm doing with my game entities. Okay, so great. We can wield some algorithms by changing the behaviors, utilizing a tool like a function pointer. Let's wield data structures a little bit here. And think about, okay, so again, I've got this same game entity here. We've got some different behaviors that we can change here. But what if I wanted to alter these other fields here? So game entity has things like health, it's got power. What if we wanted other attributes beyond those? How could we extend this struct, so to speak? So we've got a lot of data structures that we can choose from to think about how we pack in data into this struct here. Different types of arrays, hash tables, link structures, and so on. We're just going to, in this talk, again, focus on using a dynamic array or a map, hash map dictionary associative array, whatever you prefer to call it. Those are the only two that we're going to focus on today. Again, another semester-long course, probably, again, familiar with this audience on what types of things you're going to choose here. But let's look at the simplest way to kind of play with our data. Let's say, okay, we've got this game entity here, and I've removed the behaviors for simplicity. We'll still want a name so we can uniquely identify it, but now I want to start adding in components into the game entity. So those components will be the actual data that we're going to pack into the struct. And again, at runtime, I can change per entity, per what task it's going to do, and add the different components that it needs, the different data associated with this particular game entity. Okay, so we can again do this or append these different components to our game entity. Now, the constraint is at this time, well, everything has to adhere to this common interface here, this interface for what a component is. So, if this carries any sort of requirements with it, well, again, those have to be added to each game entity. So we're still a little bit constrained here. We've gained some flexibility, but how can we, again, unconstrain ourselves? What could our tools be, or how could we look at this component pattern a little bit differently? Well, one thing we could do here is say, let's not just add any component into our code, let's just be able to add any type. And again, sort of get rid of the type system. So let's revisit our tool union, which we looked at earlier, and see how that could help us. Because again, we saw unions, this sort of interesting type where we could treat things as integers, we could treat them as strings, whatever's packed into this union type. Again, just for the simplicity here, ints and strings is interesting. And basically what I'm going to do here is create my own type of var. For folks who like JavaScript, right? var, we'll just take that as an example type name. Meaning that, okay, now I've got this type that can be anything. And here's sort of the structure here for that. Again, I want to keep track of the type, so I have some information. Let's give ourselves a little bit of help here about what's in the union, right? We can tag it. And then constructor, again, for setting up and populating this type. And then the rest is just kind of machinery. Again, this is a little bit D-specific. Our operator for assigning here. And then a little bit of magic within op_assign here to test what the type is, maybe update the type or make sure that we're assigning integers to integers and so on. Okay, so there's a little bit of magic here. I've been pretty explicit in how I've set this up. I've got static if statements, which are at compile time. Again, just making sure that if what our union is defined as an integer, it's assigned to things that are integers. Okay, and here's an example of how we would use this. So we've created our own type now at line 92. It's a type of var, and we can associate it with that type here. I can tag it when we create it, and it's got a name, my integer. That's the name of that variable internally, and then we can just use it simply like at line 94, assign it to something like 7 because it's an integer, and line 95 is just the very explicit, again, going through the union, accessing the integer field, and assigning it to the same thing. Okay, so I sort of get the idea. Great, we've added a type that can hold anything into it. So this would be similar to your any types, your var types in dynamic languages, et cetera, et cetera. Okay, so great. So now, how have I unconstrained myself? Well, before we were able to add any type of component to our game entity. Now, basically, what I can do is create any type of struct that I want, and then just add more of those types of structs to my entity here. So what's going on in this code? I just call this a runtime struct, because it's something that we would be creating at runtime. At line 75, how to parse that, this is our associative array, or dictionary if you prefer, where the key is the string. That's going to be our unique name, my integer, my string. And then whatever value it holds is in var. And that's just a unordered map of those fields. Okay, give yourself some helper functions to add fields and create these structs, and voila, you've got some way to pack data together in these runtime structs, and then you can add those to your game entities. So pretty neat. I think that's pretty cool. That's kind of a magical sort of thing. We've unconstrained ourselves because we can just add any sort of type. But again, we've really unconstrained ourselves, so there is a cost to this now that we're going through this data structure to access our fields here. Okay, so for performance, I mean, we'll talk about why this might be interesting depending on what you want to do, but there are always performance trade-offs here. Now, and again, yeah, where I use this, where I've personally used this, is if you're using scripting languages, if you're taking in user input for some sort of data description language, like something kind of building up a database or a record of sort, right? You can use this because you don't know what they're going to put in here. At the same time, you don't know what you're going to put in, so you want to validate and maybe sanitize how that works, but this is kind of neat here. And bonus points, one of the reasons I'm using D and even C++ as we get reflection these days is it can start to do some interesting things at compile time to actually set up these runtime structs at compile time and use like a string mixin in D and actually just generate the concrete type if you want as well. So again, you can play with this sort of stuff. We're not focusing as much on the compile time today, but that might be an interesting thing to go from here in this talk if you're interested in this. Just by curiosity from the audience, how many folks have built something like this, a runtime struct, or maybe just use something, okay, or maybe like use a std any type or something, or just like, oh yeah, grab it off the shelf. Okay, great, yeah, you have it, but now we can kind of see where it's derived from. And the fun part is if you derive these from scratch, then you can start adding in your own constraints for what those types could be. Could it be anything, et cetera, et cetera. All right, so let's get to kind of wielding everything, data structures plus algorithms. We saw that in the abstract here. What was that? I got to give you another book to read. How many folks have actually read or own a copy of this book? It's a classic by the late Niklaus Wirth. He shows you how to build like an interpreter and a compiler in the book. It's really still a fantastic book, right? This stuff doesn't go away here. But what's kind of interesting, again, when we think about what makes up a program, right? We've talked about the data structures, and then, of course, the algorithms, behaviors that equal the programs is, well, how do we unconstrain the program part here now of this equation? So let's think a little bit about that. So again, programs themselves really are data. This is where we started the talk out, thinking about, okay, we have these bits that we can sort of shift around and shape. So our code really is data. Now, again, our operating system is going to probably give us some constraints on what a process is, what segments we can read and write to, and so on. So for instance, many of us work in compiled languages. We can't just change the text section, at least not easily, right? We can do some fun tricks to, again, add in code or load in libraries and so on to sort of change the behavior. But what if I could, again, just treat my program as bits and then change the execution from there? So how do I do that? Well, okay, let's start thinking about unconstraining our programs and playing around with them. And let's just sort of start from this standpoint here. So we learned a little bit about object-oriented programming. We learned this interesting component pattern where everything's a component. Okay, let's just make everything a command. Right? We can have this sort of common interface here from line 7, 8, and 9 here. And everything that we want to do in our particular program, it's going to be some sort of command here. Again, being a little bit violent, we want to attack. Okay, we want to move. Give somebody a hug, maybe something nicer. And then maybe, exit our program, maybe jump somewhere else in our program, right? So we can start defining these instructions here or behaviors. And again, bonus points if you want to add like a runtime struct or something in the command so you can play with the data. But let's just kind of start from here. So we're going to unconstrain our program here. And what does this look like? Well, now maybe our program execution looks something like this, right? We just have a command queue. This is pretty similar to how our machine operates, right? We have a set of instructions and a program counter that just kind of goes through each of those instructions. And every time I want to do something, I'm going to allocate, new attack, move, exit, move. Okay, we'll never actually make it to line 35 because we'll have exited, but that's the sort of idea here, right? Where we have these one command after the other that we're just going to queue up here, and that's going to be our actual execution of our program. And then it's just a loop, again, while there are things to do in our command queue of taking each of these commands, popping them off the queue, and then calling .execute on those particular objects here. My while loop condition is doing a sort of cast against to say, okay, was one of those commands an exit? If it is, then actually terminate. So that's why that line looks a little bit wild. But you could just do something more simply as saying, when my command queue's empty, there's nothing left to do, the program must be terminated. You can kind of, again, play with this. So anyways, this is kind of interesting here. And the power that we get here, and you can see the result. It's going to be attacking, move, and then we hit exit, and we just terminate our program here. So that's the sort of result here. And again, this has a name. This is a known pattern. Again, I'm not inventing this, but it's been handy. It's like a command pattern. Okay. Now what's kind of interesting is you can add execute, you could add undo, you could not pop things off the queue and sort of move backwards in history if you wanted. So again, this gives us some options or some flexibility about how we might want to do things. And you could even think about processing these in batch, maybe grabbing a bunch of commands in another thread and sort of distributing the work here. But now I have an interesting way that I can sort of execute my program here. What's the cost? Well, I'm wrapping everything in an object. Maybe we want to do this, maybe not. But it gives us a history and a provenance of our program. Okay, interesting. Or I think interesting. Okay, so let's unconstrain this a little bit more here and say, okay, we've got this, again, same thing we ran into before where we have these commands, we have to adhere to this interface, and basically I want to be able to just feed in anything into that command queue. So I'm going to use our same old tools, nothing complicated. Everybody knew what struct was when we came in here. But we have a command here. And then I have, again, at line 47, just some function. What is this? This is just a function pointer here. Okay, type of, okay, I cheated a little bit here. You'll see what a attack is. Again, for my C++ folks, this is like a decal spec. It's just picking out the function signature of anything that matches attack here, which we'll see. And then I've got a payload here. And the payload is the parameters, again, that we're going to pass into the function, or the arguments, okay? So again, we're just sort of thinking about or coming up with this protocol for what a command is. Some function, and then the payload that's going to be used within that function. And then again, this is still following the command pattern. So what we're going to do is, again, execute. And maybe we've already supplied explicitly what those arguments are, or maybe we want to pass those in a function as the arguments here. Okay, we could even go further and pass in more behaviors here, just like we learned, but ultimately we've got control here of what our command is. Okay, and then here is the full screenshot of our sort of setup here. Command as our structure, it takes in a function, and the arguments. You could think of these even like registers if you want. That's where we're sort of building up with the arguments here. And then I've got my payload here with an argument count, and maybe we limit ourselves to 8 arguments. What are those arguments? So for those who can't see it in the back, they are of anything. Our var type, hey, that popped up again here. So I've got anything that we can basically, up to 8 arguments we can pass into some function. Okay, folks okay with that? Okay, neat. Okay, so now we can start populating arbitrary commands into, our sort of machine here, or our program execution, right? Our program is just data, so let's just kind of populate this command array here. And the first thing we're going to actually sort of populate it with is, I call it a bytecode map. So I just kind of want to think about every time I create one of these commands, maybe it's something unique, maybe it's something I want to reuse. But I'm going to append a command here, one for attacking, again, the aggressive example, and one for just moving around. Okay, and then it's going to take in a payload, 1 argument, and a payload, something that takes in 2 arguments. Okay, a little bit of a D programming language thing. 1 and 2 is matching the argument count there. That's what that's populating the first. That's the constructor, basically. So if I go back here, it's matching the arg count here. Even though I haven't explicitly, you don't see the this constructor there. Yep. So I'm going to be able to take in a function, pass in 1 argument, function, pass in 2 arguments. Okay. Now, here's what our machine then looks like, right? So similar to if you looked at the assembly or, for non-compiled languages, right? This is exactly what we've done. We just have some machine instructions here. And for now, they're even a little bit blurry here, which doesn't help, but I just see some numbers here, 0, 7, 1, 5, 6, 0, 3, okay, so what is this program doing? I'm claiming this is a program now. It's just this list of integers, right? And again, for those of you, again, coming from Python or some bytecode language, you're going to say, okay, yeah, we know what these are, Java. That's exactly what it is, but I've just encoded the commands and the arguments into this stream of integers here. Okay, simple enough. Okay, so again, how to interpret this? 0, I got to read in the first value here. That just indicates in these lists of commands that I have, give me the 0th index. What is the 0th index command that we made, right? We were creating sort of these, I'm calling them bytecodes. I could have called them instructions or behaviors, but in this map, it's saying, hey, grab this thing here, right? That's the 0th command that we want here. So let's go ahead and grab that. And then their payload was 1, so we need 1 argument. What's our next argument? Well, we got to advance forward 1, okay, to the next machine instruction, which is the number 7. Okay, so I'll just walk through that again just so you can get the idea here. We have our stream of instructions. First thing's got to be an instruction. Give us the 0th command, and then pop off however many things we need for our payload. So pop off 1 thing. Okay, so you see the arrow move. All right, and then once we have our argument, now we move on to the next opcode, next operation, next instruction, 1 here. And then we say, okay, 1, where does that map to? The first index of our bytecode map, that's this thing here. The second thing that we've appended, first index. How many parameters do we need? Well, what's our payload? 2. So pop off 1, 2, okay? And then we have our arguments there. Okay, so that's kind of neat here. And then we continue onwards and onwards and onwards, okay? And we're gonna assume our machine instructions is correct here, right? They're just numbers. They could be other things too. They could be strings, you know, whatever else we wanted to pass in here, right? Any type here, but integers to keep it simple here. And then, you know, what's the rest of our program look like here? Well, again, it's basically just a loop that says while we have instructions to execute, keep looping through, popping off the instruction, and then however many arguments that we want here, and then execute. What are we executing? Well, whatever behaviors that we've tied to each command here. So again, we're back at the command pattern, but in sort of a flexible way here, where now I can just pass in arbitrary programs. Here's the whole thing, like line 78 here. Okay, this is a program that moves, it attacks, it moves, it attacks again, and then it moves 1 more time. Okay, but it's just a few instructions encoded there, and they could mean sort of anything depending on what you're doing here. Okay, so what's this? Well, this is, again, a sort of, we've basically just built a little mini virtual machine, or it could be something known as like a bytecode pattern. And again, this is all our program is here. Okay, it's just data that we've tied to specific behaviors, but now we can kind of do anything and redefine the behaviors and so on. And I think that's kind of neat. That's kind of fun to play around with and say, hey, now I have a program that can do basically anything that I define here with any sort of types that I push in here. Neat, totally dynamic. Great, we've reinvented like Python or something here, which is kind of neat. And this is, again, incredibly useful if you want to queue up work. Again, if you have some sort of interpreter need within your programming language. Again, in a gaming context, we would use this for like the scripting or modification of a game, maybe programming the artificial intelligence, AI in the sense of characters thinking in a game, for instance, with these instructions that sort of execute in a loop. And this is sort of also how we might think about batch processing and sending commands to another device, like a GPU. We're figuring out what command are we going to execute. Here's the payload, and then shipping that off to the driver here. So we could sort of have these virtual instructions here. And then again, as I said, we were going to kind of go full circle. This kind of looks like, again, what we started with on the right side, right? We're kind of back to, okay, we just have a bunch of numbers and instructions here. So maybe that's not so strange of a language after all. It's totally unconstrained. We've gone full circle here. We can do anything, define any command, and again, just sort of play with our data. And again, by the time we get to the left example, we've we don't really have our type system. We've gotten rid of that, which may or may not have been a good thing. So there's some trade-offs, but anyways, I think that's neat here. So we've looked at a lot of different things here. Again, many things that we've known, but sort of built up to, just manipulating, playing with bits, swizzling, unions, structs, object-oriented programming, different patterns within object-oriented programming. And ultimately, by the end of this, built maybe something that will be interesting for you if you have these sort of dynamic needs here. But again, your machine's just data, and you can play around with it. So hopefully I've inspired you, at least in one of these examples, to go try it, play with the code, implement it in your language of choice. Now, again, these things aren't for free, but again, you shouldn't be necessarily constrained by your language, again, because it's all just bits, it's all just executing on the same machine. So again, you can define these sort of structures as you want. Now, the thing I didn't talk about very much, but I do want to mention is, what's the performance of this? Well, of course, it's going to be much faster to just execute the native code, right? You probably want to do that, again, depending on your domain. But again, if you need the flexibility or extensibility in your code, having some versions of these with your chosen compromises is probably a useful thing. So anyways, I hope this talk invited you, or inspired you rather, to play around a little bit, try something, try building some of the tools that you've seen yourself, and see what things you can do to unconstrain your programs. All right, happy to take questions, and thank you again for having me, NDC Toronto.